All right, hello and welcome back, everybody. Today we're moving on to section 2.3. I'm calling it Fourier series in D dimensions. We're actually going to spread it over 2 days because I have a lot to talk about here. In particular, the Fourier series is really applicable to all sorts of fields that don't include PDEs, but of course they are very applicable within PDEs themselves as well. So basically, I'm gonna talk on a lot of motivations outside of the realm of PDEs as well as within PDEs, which is why I'm going to spend 2 days on this subject. So if you've seen, maybe if you've taken my course, ODEs done right instead of PDEs done right, you would have been introduced to the Fourier series already. In the case that you haven't taken that, the way that we computed the Fourier series back then was we had taken a Taylor series like we have here. So you take some sort of a Taylor series and you evaluate the Taylor series along, you would evaluate this x along the complex unit circle. And the complex unit circle, if I have a vector x, would be a vector of e to the I theta 1, e to the I theta 2, dot, 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 all the way down e to the I theta d. So you have d different thetas, right? So this can be associated to a d-dimensional theta vector, theta 1, theta 2, and so on, theta d, where theta is describing the angle at which I've traveled around the complex unit circle. And if you make that change of variables of the x's to the complex unit circle, and then you assign the variables theta 1 through theta d as your possible variables, you can actually do that with the negative thetas as well. And what you end up with is a series that looks like the following. So we've got the series here. These would basically be the Taylor coefficients. And then the other terms coming from the complex unit circle would look like these complex exponentials. And then in this case, instead of using the variable theta, I've used the variable x. Okay, so x describes an amount of rotation in the complex plane. So you can think about it like this. Here's the complex plane. We have the real numbers. We have the purely imaginary numbers. And the complex unit circle starts at 1, ends at 1, and you end up with I up here, 1 over here, negative 1 over here, and negative I over here. And the power of e to the I theta gives you some point on this circle where the angle from the positive real axis is the angle theta. So this x, because it's in the power of an e to the I, and then we've got some frequency terms here, but because it's in the power of e to the I, some frequency in x, we're really describing the amount of rotation we have in the complex plane. Now what's happening here is we have, for each x then, so there's my x, is the input to my actual function. For each x, we rotate a different amount. And for each n, here's an n, in the sum, this is why it's called the Fourier series, because I have a sum here, n going from minus infinity to infinity. For all of those n's in the sum, in fact, the single x that we decide to put in here rotates this by a different amount. So we get a different rotation for each x that would go into f, but we also get a different rotation for each n that's in my sum, and I'm going to add up infinitely many of these rotations, starting at minus infinity and ending at plus infinity. And depending on the coefficients I choose here, I can construct different selections of f. Okay, and I'll link to a video by 3 Blue 1 Brown where he shares really what's going on with this Fourier series. You can think about these, since they're rotations around a circle, as periodic, okay, cosine sine waves, and we're adding infinitely many. So you add infinitely many cosine and sine waves of infinitely many frequencies to reconstruct the function f. Now, how do I know I can actually reconstruct the function f? Well, what I have to do is I have to start with a condition, and that's that this function f needs to satisfy what's called square integrability. And I did cover this all the way back in section 1.1 when I was talking about sets of functions. This was a common one, square integrable. I also called it L2. In this case, it's L2 of this interval x0 to x1. That means square integrable functions. And what I need is that if I square the function, if it's complex valued, you have to take the magnitude squared. We want this to be purely positive, and squared. If I take that function and I integrate it over some bounds, as long as that integral exists and is finite, then we call ourselves square integrable. A lot of people are curious about what sorts of functions actually fit into this. Let's just choose 0 and 1. So let's let my x0 be 0 and my x1 be 1, so that that interval is 0 and 1. A very common function that's not going to be square integrable would be the function 1 divided by x to the 1/2. Because if I square that function, or 1 divided by the square root of x, same thing, right? If I square that function, I end up with 1 divided by x dx. The antiderivative of 1 divided by x is the natural log. Evaluated at the bounds, we get the log of 1, which is totally finite, but the log of 0 is negative infinity. And so we end up with positive infinity for this integral, which means that, this is not square integrable. And so we won't be able to use the Fourier series on a function such like this. And some people ask, okay, now give me an example of a function which is, or even one that's really, really closely related to the one that I just gave you. Let's do 1 divided by x now to the 1/3 power. If I make it 1/3 instead of 1/2, when I square that function, I get 1 divided by x to the 2/3. And the antiderivative via power rule gives me 3x to the 1/3. And if I evaluate that at both bounds, I end up with 3 minus 0, which is very much a finite number. And this exists. So you get this 1 over x to the 1/2 really is kind of the cutoff. You can think about it that way in fact, this function even blows up at 0. If I were to plot it, how does this look over the interval? It still blows up at 0, but it blows up slow enough that it's actually still square integrable. And that gives me the ability to write a Fourier series for that function. So how do we actually write the Fourier series? I haven't told you how to do it yet. I said depending on these coefficients, right? So depending on these, we know how to reconstruct f of x, but how do we find them? They get defined as the following. They're just defined as integrals. And I'll call it defined as normalized integrals against complex exponentials. Okay, so really what we can see here is here's a complex exponential. This was how I was reconstructing. And here's a complex exponential. And so they both play a role in both sides of my Fourier series. But the only difference, we want to comment on the one difference between the two, is that this I is a positive I and this I is a negative I. Okay, so these are complex conjugates of one another. They're complex conjugates of one another, and in fact, anytime you define the Fourier series, you have to make a choice over which one of the two you want to be positive and which one of the two you want to be negative. So I've made the choice to let the reconstruction be the positive I and the evaluation of the Fourier coefficients to be the negative I, but in fact, anybody can make the choice as long as you stay consistent. But this is actually how we would construct these coefficients. And we have a name for all of the coefficients if we not add them all together, but if we group them into a set, or even as a function, if we call it a function from the integers into the complex numbers, right? Because it's input n. There's n, my inputs. These are all of the integers. So considered as a function from the integers to the complex numbers, it's called the Fourier series transform over its respective interval. Okay, so it just gets defined as this integral, and I want to comment, because this is sometimes confusing for students right away, I want to comment that the original f showed up here, right? And the variable there was x, the variable in the complex exponential is x, the variable we integrate over is x. So if we're integrating over all of x's, we integrate over all x's and end up with a function of n. So the function of n that we end up with is coming from the n in the complex exponential. So you have to leave that. You have to manage to compute this integral while leaving n as just a constant in the power of the exponential. But if you can pull that off, if you can find the integral leaving n as a constant, then you've found your Fourier transform, which depends on that n. So let's actually, I'm going to scroll down and we're going to actually compute one of these. I'll talk about the next lemma in a bit. But I'm scrolling down and let's see actually how to compute one of these. So the Fourier, let's take the Fourier, and I'm going to call it the Fourier series transform. A lot of people will just call this a Fourier transform, but it's a bit of ambiguity with what we'll encounter in section 2.4, also called the Fourier transform. So I'm going to call this one the Fourier series transform because we really are constructing with a Fourier series. And we're going to try to actually evaluate it for the function x cubed, and all of these are attached to an interval. So I want to comment on that right now. Every Fourier series transform, or every Fourier series, is always paired with an interval. The same way that we would pair every Taylor series with its center, right? A Taylor series doesn't make sense until you choose the center. The Fourier series doesn't make sense until you choose an interval. And so we always need to be given a function as well as an interval, and then we're going to be able to compute it. And the interval shows up, if I go back to my definition all the way here, the interval shows up here, 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 and here, 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 here. Okay, so the interval, whatever interval we choose from interval given. Okay, so somebody's going to give you an interval. There it is, x0, x1. Every single x0 and x1 that shows up in every single one of these definitions gets replaced with the x0 and x1 from the interval from the beginning. So this is why if I jump all the way to our example and I say we're looking at the interval -1 to 1, I've replaced every x0 and x1 with a -1 and 1. And then in the next line here, I've simplified all of those, and we end up with a much easier integral than it initially looked like, right? I think it's perhaps a little intimidating to see, oh, I have to calculate this complicated integral. And yeah, it looks complicated there, but once somebody hands you f, they hand you x0 and x1. In fact, the integrals that you're going to be computing look like this. It's not easy. It's not going to be, the world's best integral, but it's not going to be anything too complicated. And I want to remind everybody before we get calculating too much that the antiderivative of e to the ax dx is 1 divided by a e to the ax plus c. And of course, in these sorts of problems, because they're all definite intervals, we can just forget about c because that would always get canceled out. So we want to think about every time we're taking an antiderivative of e to the ax, we're going to group all of these terms in together and call that a. There's my x term sitting right next to a. And when we find its antiderivative, we're going to get something like 1 divided by -I pi n. Okay, e to the -I pi n x. So every antiderivative of e's that we're going to see is going to look something like that. And this is the integral we're actually going to try to compute. To compute these, this is slightly unfortunate, depending on if you were in Calc 2 or Calc 1 when you covered integration by parts. The way to compute integrals of polynomials multiplied by something else is always integration by parts. And so if you are feeling a little rusty on integration by parts, I think you should go ahead and look up some videos on how to do that. But here's a polynomial, x cubed. It's been multiplied by my exponential. I'm going to have to use integration by parts here. You always want to call the polynomial will be u. So you compute du in int by parts. So you're always going to be taking derivatives of the polynomial because that's going to reduce the power and eventually let you get to your solution. So we're going to do some integration by parts here. If I do one round of integration by parts, I call x cubed u, and I call my exponential v. So let's say this is u. Let's say this is dv. Sorry, it's u dv in integration by parts. What does this equal? Well, it equals uv minus integral v du. We have to figure out what each of those are. If x cubed is u, there's my u and my uv part. If the exponential is dv, I need its antiderivative to go here in v. So the antiderivative of this exponential, I just covered it. The antiderivative of the exponential is going to be the exponential divided by whatever is multiplying x on the inside. So this is my u dv, or sorry, my uv. And then I've got my minus sign. This will be my integral of v. Sorry, my integral of v is here. Du is going to be the derivative of x cubed, which is 3x squared. So this is actually du times v. But however you want to think about it, this is one round of integration by parts. And so we're going to go ahead and compute the one round of integration by parts. It only lets us compute this portion, which I do against the bounds, and I end up with the following. The second half needs to come along for the ride because I don't know how to compute this yet. So I'm going to keep the second half along for the ride and compute the first half of my integration by parts. And a lot of you may be wondering, what in the world is going on here? How can I simplify? So how can I simplify those complex exponentials? I'm going to remind everybody of Euler's formula. This will be invaluable for us the entire time with Fourier series. The first one's going to be cosine of negative pi n. The second one's going to be cosine of pi n, and that's just the real parts. The imaginary parts are going to be plus sine of negative pi n. The imaginary part's going to be, I sine, plus I sine of pi n. And then we're going to have to use our regular unit circle to simplify those. So if I scroll down a little bit, I say that using our regular unit circle to simplify those, let's recall what the unit circle looks like. Regular unit circle in the xy plane. If I go by negative pi n, recall that n equals 1, 2, 3. It also equals negative 1, negative 2, negative 3. So that's moving exactly pi radians, either clockwise or counterclockwise. But no matter which choice I make of clockwise or counterclockwise, I end here on odd n, and I end up back where I started for even n. Okay, so that means when I'm odd, I'm negative 1. When I'm even, I'm plus 1. How can we simplify negative 1 and plus 1? It's negative 1 to the nth power. A lot of you may be saying, okay, why did sine disappear? Well, if we go back here, what is the sine value here? That's the y value, 0. What is the sine value here? That's the y value, 0. So we only have the cosine term showing up as negative 1 to the nth power. In fact, we recover the exact same for the positive pi n's as well. So we can simplify both of these to negative 1 to the nth power. That is these terms. You'll recall just the numerators, but those terms. And so if we simplify the numerators to negative 1 to the nth power, we end up here, and we can add those together. If we add them together, we just get a 2 on top. 2 on top is going to cancel with a 2 in the denominator, and we end up simplifying it to negative 1 to the nth power divided by negative I pi n. So that's what one round of integration by parts gets me, and lucky me, I get to do it again with the integral I have left over. So I do integration by parts again on the integral I've left over. That's this one right here. I'm going to choose u as x squared, dv as the complex exponential. Now I have uv minus du times v. And once again, I can evaluate the uv term. I cannot evaluate the du times v integral. So I go ahead and evaluate the uv term on its bounds. And when I evaluate, I have to use, Euler's formula again on these complex exponentials. I end up with negative 1 to the n. In this case, I end up with minus negative 1 to the n. So these terms actually cancel, which is why I've got the cancellation line through there. Those terms cancel when I make that evaluation, and I'm left with just this one integral sitting around still. I'm going to have to do one more round of integration by parts because I have an x times a complex exponential. So going through one more round of integration by parts, everything else is coming along for the ride, but I still have this one integral of x times a complex exponential. We're going to do one more integration by parts. I'm going to choose that x is u, the complex exponential is dv. Over here, I've got u times v minus, now du, when x is u, if I'm taking a derivative of u when x is u, is just dx, and so there's my dx sitting around right there. So my last integral, I can finally compute that one because it no longer needs an integration by parts. I also know how to evaluate this one on the bounds because there's my complex exponential. I can use Euler's formula for that. X will just be plus or minus 1. And I make all of those evaluations as the negative 1 to the n plus negative 1 to the n again. Simplify a few of those terms. This integral, I have to compute as well. That's going to be right here. I add everything together, simplify, go through some cancellation, and we end up with the following. So here's the Fourier series transform of x cubed over the interval 0, 1. This is of x cubed over, I said 0, 1, but it's actually negative 1, 1. Okay, so it's a lot of work. You have to put in that integration by parts work over and over again. But there's a reason why you were taught it. Nobody was expecting to teach you integration by parts and then you never use it again in your life. I mean, maybe you were expecting to use that, but everybody else who was teaching it to you taught it to you for a reason. So it's time to get good with integration by parts. And we have our answer here, which I've simplified a little bit. Okay, so I've simplified our answer by factoring some terms out. Totally fine. But let's be careful. This is when n is not equal to 0. That's not a factorial. That's an exclamation point. So this is specific to the case when n is not equal to 0, because if n were equal to 0, divide by 0 is not good. So we don't want to divide by 0. We have to encounter that case separately. It's not too bad. If I just go back to the definition of the Fourier series transform, let's go all the way back to the beginning. Fourier series transform is here. The definition when n is 0 is me putting a 0 in right here for n, and anything to the 0 power equals 1. And so the definition for the Fourier series transform specific to the case of n being 0 will always just be the integral of the function itself times 1 dx. So it's really just the integral of the function itself, also known as the average value of the function over the interval. And so if we're going to compute that in this situation, we need to encounter that case separately. I will just go ahead and compute the integral of x cubed dx, and I end up with 0 because it's an odd function over symmetric bounds. And so we finally recover the true Fourier series transform of x cubed over this interval as the piecewise function that differs when n is not equal to 0 versus n being equal to 0. So this is useful, keep in mind, because recall then that x cubed should be equal to the following series: f hat n, as given on the left, e to the I pi n x, when n ranges from minus infinity to plus infinity. So we're expecting something like this to be true, and if I scroll down, I can go ahead and plot it. And we've plotted it now. Let's see what we've plotted it for. We've plotted it for plus or minus 5, plus or minus 25, and plus or minus 125 terms in the series. And we can see that when we add so many terms together, we are truly encountering, this was my original x cubed function in gray. Everything's passing through. And the really, really jagged terms, but also the ones that approximate x cubed really well, those are the 125 term sums. So this is just an alternative to the Taylor series where we can approximate functions within some interval. I do, however, have a remark, and it's not this remark, it's the second remark. I have a remark about something called the Gibbs phenomenon and the periodicity of reconstructions, okay? So we want to be careful with everything we just saw above. And what have I seen here? What I've seen is that, yeah, we have a really, really nice approximation for x cubed, but this approximation occurs in a very specific place. Let's figure out where this interval is. Jump up. That's the interval from -1 to 1. So I have good approximation on the interval I calculated. Right? Between those bounds, my approximation is actually very, very good when I'm using 125 times 2 plus 1, so 251 terms. My approximation is very, very good within the interval, but all of a sudden it actually jumps. Right, my approximation, my terms in purple, red, and orange, that has now been inverted for everybody, but my terms in those colors all of a sudden jump and in fact are periodic. So if I extended this graph farther, these would just jump and they would look like this curve that I'm tracing out over and over again. So they would just repeat this x cubed curve over every interval. And so that's called the periodicity of reconstructions. And we also have what I was referring to as the Gibbs phenomenon. The Gibbs phenomenon is just this extra oscillation. So the fact that we have extreme oscillation at these boundaries, this is called the Gibbs phenomenon, and it just reinforces the fact that we actually don't recover the convergence in the way that you're probably very used to convergence happening. We don't recover pointwise convergence. So there's going to be a collection of points. Often they're near the boundary, but there's going to be a collection of points near the boundary for which actually the Fourier series doesn't converge. This isn't the sort of convergence we care about. The convergence we actually have is convergence of difference in area squared And we don't actually usually call it difference in area squared. Mathematicians have a name for this. It's called L2 norm convergence. Norm convergence. So mathematicians have this word L2 norm convergence to describe the convergence of a difference in area squared. And so if we look at the area in which the gray line and the purple line, inverted mind you, differ, the area is so small. Right, the difference in area here is just negligible almost everywhere because these areas between the two are so small. And so it's that area that converges to zero. But you could imagine if you have a really spiky function, the area underneath a spiky function can still be very small, and it can still tend to zero as the spike grows infinitely large. So it's this notion of the area tending to zero that's special about Fourier series, and not that pointwise we're able to approximate a function. We care about its area, which is very useful for differential equations because areas are directly related to integrals and the solutions to differential equations. How do I invert a derivative with an integral? So this is really useful for differential equations. It gives us a concept of something called weak solutions. To have this sort of convergence of solutions in area rather than pointwise solutions. So this is something that's just should be pointed out about Fourier series, is that you don't get convergence the way that you would expect with the Fourier series. You don't get pointwise convergence, but rather you get this convergence in area squared. And that's how you would plot a reproduction, right? So here's my function of x cubed. I've just literally grabbed the coefficients that I just calculated above, went through all those integration by parts for calculating above. I've grabbed all of those and multiplied them by their respective complex exponentials to produce this graph. And as long as you use symmetric bounds, you'll never have to worry about complex numbers showing up. All of the negative imaginary terms will cancel with positive imaginary terms, and you'll recover a perfectly real solution as long as you make sure n is symmetric around zero. I also have a remark about integration by parts and Euler's formula. Of course, we just kind of experienced that, so my remark is saying don't forget integration by parts, don't forget Euler's formula. So I'm not going to cover that anymore because I did just talk about it in the exercise. Instead, now I'm going to head toward this lemma. Okay, so I should say that when I introduced the Fourier series right away, I introduced it as a theorem. And the reason being is that, I'm making a pretty strong claim here, just because you could argue that this is a definition of the Fourier series, but the fact that this one function is equal to the summation is actually a really strong claim. So that statement that I've just highlighted is the Fourier series theorem. So this does need a proof. And to prove this theorem, we need the following lemma, which is known as Parseval's identity. So it's got a name, Parseval's identity, or sometimes Parseval's theorem, or sometimes even the Plancherel theorem, which is usually reserved for even more powerful cases than this. But what this theorem says is something really, really nice and elegant. It says that suppose that I have a function which is square integrable. And remember, that just means that when I square the function, it integrates to something that's finite. And that means that I have a Fourier representation, but we haven't proven that yet. I'm just saying, out of the blue, suppose I've got a function that exists and is finite. If I define this collection of numbers, which really is the Fourier series transform, but supposing that we don't even know it equals the Fourier series yet when we compute the Fourier series, I'm just going to construct a collection of numbers. Just construct this collection of numbers. And even though, me being older and wiser knows that this will give me the Fourier series, I'm just going to call it a collection of numbers. Then in fact, this collection of numbers satisfies a very specific identity. And if I sum the collection of numbers squared, in magnitude squared, so I'm going to sum it over all n's in magnitude squared. In fact, that sum is a convergent sum, and that convergent sum converges exactly to the average. Okay, so I've divided by the length of the interval, so it's the average of the square integral function I started with. So you can either take a function, square it, and integrate it, or you can compute this massive collection of numbers, square all of those, and sum them. So there's this really beautiful relationship between square infinite sums. So square infinite sums and square integrals. And in fact, this relationship is one of the most powerful tools that Fourier analysis gives us. You can discover some really fascinating identities because of this this relationship. We can form a really strong relationship between integrals of square functions and sums of square functions, and the functions are related to each other through the Fourier series. So this is called the Parseval's identity. I don't prove either the Parseval's identity or the Fourier series theorem in this video. It's proven in an appendix at the end of the chapter, so if you're really interested to see the proof, just head to the appendix and I cover the proof of both of them. But I introduce both of them because we will use both of them. Okay, so certainly we'll use the first one because that's kind of the whole point of the chapter, but the second one we'll use in some of our motivations. But I'm just going to scroll down now and give you one quick motivation, which is how I'm going to end this section for today, is going to be using the Parseval's theorem or Parseval's identity to extract exact values of the Riemann zeta function. Okay, so this is not even related to partial differential equations. It's actually just something that I find really fascinating about the Fourier series and Parseval's identity, and that's that we can extract exact values of this very, very particular and very special function known as the Riemann zeta function. We can do it for positive even arguments. Okay, so what is this function, this Riemann zeta function? It looks like an infinite sum. Everybody liked infinite sums back in calculus 2. And what am I summing over? I'm summing over 1 divided by n, okay, that's the argument of the sum, 1 divided by n to the s power. And this s power here is the argument of the Riemann zeta function. Okay, so I'm looking at, for example, zeta of 1 is just going to be n equals 1 to infinity, 1 divided by n to the first power, which is 1 divided by 1, plus 1 divided by 2, plus 1 divided by 3, plus 1 divided by 4. And if your calculus 2 instructor was worth their merit, then they would have told you that this is an infinite sum. It doesn't converge. It's a divergent sum, and is known as the harmonic series. Okay, so we've just found out that the Riemann zeta function evaluated at 1 is infinite. But what about some other values? Zeta at 2, for example, would look like n starting at 1 to infinity, 1 divided by n. Now the power is 2 squared, so this will be 1 divided by 1 squared, plus 1 divided by 2 squared, plus 1 divided by 3 squared, and so on. And in fact, this was a very famous problem that was solved by Leonhard Euler way, way back in the 1700s. He finally proved that this sum was equal to pi squared over 6. So that's a really exciting value to come up with. But we should talk about maybe why this function is important in other ways. It's directly related to finding the prime numbers. And I can't really get into how it's directly related to finding the prime numbers, but of course the primes are notoriously unpredictable. And in fact, there are ways, if we fully understood the Riemann zeta function, that we could perfectly predict the next prime. But that's if we fully understand it. But what that means is that it's really closely related to the distribution of primes. And if we want to talk about one open question about the distribution of primes that we have a question about is every case where the zeta function is equal to 0. So what values of s, and in fact these are values of s in the complex numbers, what values of those give zeta of s equals 0? Super open problem. What we do know is that all of the negative even numbers give us 0. But we don't know that this is the conjecture, is that every case of non-negative even numbers being 0, every other case of 0 satisfies that the real part of s is equal to 1/2. Okay, so we don't know that this is true, but we know it's true for a very large collection of zeros. And in fact, every 0 we've ever found makes this true. So this statement is known as the Riemann hypothesis, but nobody's been able to prove that it's necessarily true. So finding these values of s and knowing more about the function is a very useful thing to know in math, and in fact you can win $1 million if you prove it to be true or not true. So there's something to do next weekend if you get bored. But what we can do with the Fourier series is we can give ourselves zeta of the positive even numbers. So the zeta of the negative even numbers, I was just kind of remarking they're all 0. Zeta of the positive even numbers, we can use the Fourier series for. I'm only going to do it for Euler's special Basel problem that we have here. So we're going to go through a proof of the Basel problem. And we're going to use Fourier series to get us there. So let's do it as the following. We're going to compute the Fourier series transform of the function x. Okay? So we're going to take our function x, and we're going to compute the Fourier series transform of x over the interval minus pi to pi. Remind everybody what that looks like. F hat of n over minus pi to pi would be 1 divided by 2 pi, integral minus pi to pi. And then we have x e to the negative I n x dx. So this is really only a single integration by parts problem, which is pretty nice. And if you go through that single integration by parts problem, we get the following piecewise function. It's equal to negative 1 to the nth power I over n every time we're not equal to 0, and it's equal to 0 when we are equal to 0. So we scroll down and we use Parseval's identity. I don't want to jump all the way back to Parseval's identity, but you can go ahead and relook at what Parseval's identity said. Parseval's identity said that the integral 1 over 2 pi, negative pi to pi of x squared dx had to be equal to the infinite sum, n going from minus infinity to plus infinity, of 1 divided by n squared. And this would be also n not equal to 0, just because of what we have just calculated for f hat. Okay, because that's really the magnitude of f hat squared. So just because of what we just calculated for f hat, we know that the following identity is true. So what am I going to do? I'm going to calculate each side individually, but I don't know this. The question is, what is the right-hand side? I know the left-hand side. All of you could do the left-hand side in Calculus 1. You go through it, you get pi squared over 3. The right-hand side, right, looking at this sum, because I'm starting at minus infinity, and I have something like, dot, 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 minus 3, minus 2, minus 1, and then I skip over 0. So I go 1, 2, 3, and in fact, if I square all of these, let's square them now. So go to the squared power, and we're going to get 9, 4, 1, 1, 4, 9, and we're taking the reciprocals of all these. We have 1 over 9, 1 over 4, 1 over 1, 1 over 1, 1 over 4, 1 over 9. We end up with twice, right? This sum from minus infinity to plus infinity is actually twice the sum that this would be 2 times the Riemann zeta function of 2. So 2 times the Riemann zeta function of 2 is equal to this, but this, by Parseval's, is equal to this, and this, by calculation, is equal to that. So 2 zeta 2 has to be pi squared over 3. 2 zeta 2 is pi squared over 3, or in other words, zeta of 2 is pi squared over 6. So we've just proven / solved the Basel problem with Fourier analysis. And you could continue this actually for all even powers of zeta. So that's just a little fun thing I like to comment on every time I cover the Fourier series. Anyway, that's all I've got. We're going to continue on this section in the next video. I'll see you in class later. Bye.